Hello everyone again and welcome to my channel. On our previous video we looked at how we can generate eigenvalue, which is also called an observable, from an eigenfunction with the help of an operator. Now in this case our operator is actually our linear momentum. In classical mechanics we know momentum to be the product of the mass of an object multiplied by the velocity. Now we're going to look at how we can use the linear momentum in the quantum level and generate its observables. Now let us look at it in this particular case. Let's consider the linear momentum to be px, which is in the x coordinates over there. Now an observable is easily measured where our px, which is our operator, is multiplied by our specific eigenfunction to generate its observable, which is represented as A, multiplied by the eigenfunction, which is actually being reproduced. That is what we should expect. Now, where our operator, which is the linear momentum in the x-coordinate, is equal to negative I multiplied by h bar, or multiplied by d over dx. This is actually the operator expression for our linear momentum. Now if we put this into our equation over here at the left side, we get I multiplied by h bar, don't forget the negative sign, now all multiplied by d over dx, and our f over here actually comes in here. Now the question now is, what is our f function, which is our eigenfunction? Now where our f function is equal to e raised to the power of ikx. Sometimes this all is equal to our wave function. Well, you don't need to put the wave function in there, but I just put that there just for courtesy reasons. At least you guys should be familiar with it a little bit. But looking at it over here, what we get as a result, if we put that into this particular equation, what we get is negative I multiplied by h bar multiplied by d into bracket our f, which is equal to that, which is e I k multiplied by x, all raised to the power all over our dx. Now let's look at this formula and see the part that is our operator and the part that is our function, and how we can manipulate our function to spit out our observable, which is A. In this case, what we realize is that this section of this expression is actually our operator, because our operator is actually our linear momentum, and that is being reproduced in this case, and this particular is actually still in existence in this case, while on this other side over here is expected to be our eigen function. Now let's see whether we can regenerate our eigenfunction by performing this particular calculation over here. Now if we perform our first derivative of this inner function, let me just put that over here, what we get is, we get h bar multiplied by k, all into bracket multiplied by our original function over here. So once we got our original function being reproduced over here, what we get as a result is our eigenfunction, which is being regenerated after we perform our first derivative calculation over there, and our resulting product in here is our eigenvalue. So this is our eigenvalue, that is observed during the measurement, while this is our eigenfunction of our operator, and in this part this is our operator, which is what we started off with over here. So to actually be sure that we got this right, let's kind of do the calculation on how we got from this particular case to this particular case over here. So in the calculation, we do know that I h bar is being multiplied by the derivative of this function. The derivative of this function is ik, which is brought out, multiplied by our inner function over here. So our original function multiplied by the derivative of this particular exponent over here is our exponent constant, which is brought out over there, multiplied by that. Now we do know that how is the negative actually eliminated from here? We do know that I multiplied by I is equal to I squared, and I squared, which is also equal to square root of -1 over there, all squared, and this cancels that, and what we get is -1 multiplied by -1, which is equal to 1, and then our h and our k is actually brought back in here, which is the h bar and our k, and this is actually what we got as our constant, which is our eigenvalue over there. So I hope you're able to follow this, and I hope you're able to understand this. Please hit a comment down below, let me hear your thoughts about this, and before we actually run away by saying bye, let's just bring back our answer here. So our answer in this whole calculation that we got over here is A to be equal to h bar multiplied by k. Now where k is actually any constant, and the linear momentum is an observable that is really continuous, because for a particular operator to be continuous, we must not have a constant, or we don't need to have value of an eigenvalue. We don't need to have values for our eigenvalue, where for a discrete operator we do have our representation, which is A, which is our operator, multiplied by Fn, what is equal to An Fn, where n equals to 1, 2, 3. Why? For the other part, if it's continuous, then we just have our operator multiplied by our eigenfunction is equal to our eigenvalue multiplied by the same eigenfunction. Now in this case, where n is actually values or value of eigenvalue. So that's about it for this particular topic. I hope you're able to understand this particular example. Please hit the comment down below, let me hear your thoughts, and see you all on my next video. Peace, be smart, bye.